So let's talk about what goes in a geodatabase. Basically, feature classes and feature datasets. Feature datasets are collections of related feature classes. You can also have tables, annotation, relationships like formal persistent joins, planar topology, and network topology. Here is a nice illustration of what can be in a geodatabase, and you can look down through the list and see all the different things and how they relate to the various database connections and data and things. As far as the functional applications of geodatabases support a variety of data management functions. And the purpose of all these functions is to essentially either increase the efficiency with which you do work or increase the accuracy of the work you do. And so the big ones are domains and subtypes, planar topology and spatial rules, network topology and connectivity rules, relationships classes are sometimes referred to as referential joins, and of course versioned editing if you have a large SDE relational geodatabase. Domains are literally just rules about what can go into an attribute field. And the purpose of this is to reduce data entry and consistency errors. Domains basically have two flavors, coded and range. Coded is a situation where you only have certain answers that are allowed, and those answers are expressed in the terms of a code, like a simple number like 1, 3, 6, and 12, and a corresponding description like 1 inch, 3 inch, 6 inch, and 12 inch that relates that simple code into a more meaningful piece of information. And the reason you use something like that is it's easier to hit the number 1 than it is to type in 1 inch, so it saves time. It also means you don't have to worry about trying to hit a 1 and your finger gets out of the way and you hit the Q key and you can't put Q in because Q is not one of the codes that's allowed. Then there's the range domains, which basically sets a numeric range that your answer has to be between a set start and ending point. It will allow you to put incorrect answers in, but when you validate the data, it will flag those as being in violation of the rules, and then you know, hey, I've got to go fix that. Another similar feature is something called a subtype. Subtypes are a little different. These are integer-coded classes of features. So in that respect, they're very much like what we were just talking about. The big difference here is these are all just types within a single data set. And so they automatically display with different symbols. They behave as individual layers. Each subtype can have its own default values that you enter. And so there's lots of stuff going on, but the big thing here is it streamlines attribute entry. So in this example, you're developing roads across, say, a city or county, and you have all these different types of roads, and they have sort of set parameters. You can code all that into the subtypes, and then when you draw in the next new road that's being made, you select the type of road that it is from your subtype menu, and it populates all those attributes in your attribute table. And then you don't have to do it manually, and more importantly, you don't have to worry about making mistakes. Another good use of this sort of technology is planar topology. Planar topology just sets up rules within and between layers, things like no overlaps, no gaps, that kind of stuff. And you use planar topology during editing to make sure that topological consistency between features and feature classes is preserved, and so that when you have coincident boundaries and things like that, that they maintain that cohesive nature across the various features. Network topology is slightly different. Network topology is all about path of travel, is the way I like to think of it. You create networks to analyze traffic and utilities and any sort of things that have to follow some sort of a diagram, if you will. You can apply rules to this. In the example they have here, if you go from one size pipe to another size pipe, it has to have an adapter. And so that would be one way of mapping out like the infrastructure of a water or sewer network. And if then later on you say, oh wow, we just got a letter from the manufacturer, these couplers that go from one size pipe to another are beginning to fail after a certain amount of time. How many do we have? Where are they at? Well, you could query through your network, and everywhere that you have a 12 and a 6-inch pipe going together, where you have to have an adapter or a coupler or something like that, you could identify that because your network topology would not allow those pipes to go together of different sizes unless you physically mandated that you had that coupler or that union, that whatever it is there, that adapter, and along with that, the information about what type it is, when you installed it, that kind of stuff. Versioned editing. Versioned editing is quite possibly the coolest thing that is available in geodatabases. It's only available in the large SDE commercial geodatabases. What this does is it allows multiple people to edit a geodatabase simultaneously. What does that mean? Well, imagine there's a really bad storm, like a tropical storm or a hurricane, and it wipes out some tropical island like Haiti or the Dominican Republic or something like that, does countless thousands of millions of dollars worth of damage or what have you. In a large commercial database like this, if you had all the infrastructure, the maps, the whatever in place, you could literally have people around the world accessing that database, mapping out what's damaged, what's been impacted, what hasn't, editing, for example, road segments to identify parts of roads that are closed and things like that. There's all kinds of stuff you could be doing. The neat thing is everyone could do this at the same time and not get a file lock, which is what typically would happen if you weren't in a database that had versioned editing. The way this works is it then allows some administrator to have the ability to resolve conflicts. And so when you have this edited version, it allows you to say, okay, this we're keeping, that we're not. And you can do this to do a lot of things like test what-if scenarios. What if we did this? What's that going to look like? That doesn't look good. Let's go back to what we had before. And then you simply just roll it back to the previous version, which works good in case of failures. It also works good in case of mistakes. Schema. Schema is a full description of all the feature classes, tables, fields, topology, and relationships that's in a database. These can be grown through time as the database is assembled haphazardly, but the real benefit of a database comes from doing this sort of stuff in a more meaningful fashion with a purpose and an intent when you set it up. And so realistically, schemas, just like your databases, need to be set up ahead of time. You need to figure out what, as an organization, you need from your data, and you need to write out that schema that shows how it's all going to work together and what all is going to be included and such. And then the schema can be downloaded and shared and customized, and ultimately it's sort of a roadmap or a blueprint of the structure of your information and data within your geodatabase. Here are some diagrams of some schemas. They can be pretty elaborate and pretty complicated things. When you look right into it, you'll see a lot of information, and some of it is just basic simple stuff like what does prefix, deprefix, underscore, suffix mean, or street name, or distance, or direction, or radius. Maybe it just tells you the field type. Maybe it tells you more about it. Lots of information that people might ask that you really don't have a good, clever way of providing them systematically, except for a schema. And a schema is that place where you have that opportunity to deliver that to your customers.